Hi, I'm Jason Woodring, and this is the final presentation for my project for MEMS 5001, Optimization Methods in Engineering. So the purpose of this project was to optimize the control surface sizing for the aircraft shown on the right. There was an inner aileron control surface and an outer aileron control surface referred to as the outeron and the inneron. So I generated datasets in AVL, which is a vortex lattice method, for several thousand different positions and sizes of each control surface. The outeron was a function of two variables, its deflection and where it started along the span. It was a fully moving surface, so I didn't have to vary its chord fraction. The inneron was a function of three variables, its chord fraction, its position along the span, and the amount of deflection that it had. This made it for a 30 by 30 data set for the outeron and a 30 by 30 by 30 data set for the inneron. I would have had higher resolution data sets, but this took roughly 24 hours of processing time. Possibly in future work I might use more. So since the outeron data was a function of two variables, I used a surface fit to model each of the data before optimizing it. I modeled the drag data as a simple polynomial fit. It was a relatively smooth curve, and I used a locally weighted scatter plot to smooth the data for the yaw moment, which was the constraint for the outeron. Then for the optimization problem, I set the constraint such that the yaw moment would have to be greater than 11.5 times 10 to the negative fifth, which is a non-dimensional coefficient. And this was produced in previous research as the approximate amount of yaw that would be required for controlling the aircraft. So for the optimization of the outeron size, I just used the fmin_con function with feeding in the surface data that I generated previously, and I found that the optimal point for it was at 1196 millimeters and a almost 5-degree deflection, which gave the required yaw moment within the constraint tolerance. This then led to a roll moment from the outeron of 9.84 times 10 to the negative third, which again is a non-dimensional coefficient. That is the amount of roll moment that the inneron will have to counter in order for the aircraft to not roll when the surfaces deflect. And therefore that is the constraint for the inneron optimization. So this is the data for the inneron, and each of these plots is where you hold one of the variables constant and see how the other design variables varying affects the cost function. So you can see for the span position changing, there are several points along the span where the drag spikes. I believe this is related to the twist distribution of the wing on the aircraft. And this causes there to be several local minimums in the data series. And I needed to use an algorithm for the optimization that would be able to find the global minimum consistently. So obviously the fmin_con function would not work for this. Also, each of these data series was represented using an integer set of indices within the generated data plot, since I couldn't interpolate it as easily or quickly enough for the optimization to work. And I found the function that worked best for this was a genetic algorithm using the integer constraint option for it and parallel processing, which was able to calculate the global minimum quite quickly and very consistently. So here are the results for the inneron optimization. And on the right, I have the generation plot for the genetic algorithm. It found the non-dimensional drag is minimized at roughly 0.0049, and it found it within 50 or so generations, which only takes a few seconds for it to do. And it found that this was at 541 millimeters for the starting position along the span, and it also found another local minimum at 625 millimeters occasionally, but the actual drag was lowest at the 541 millimeter position. And they found that the optimal amount of chord fraction was 18.3% with a 2.2 degree for deflection. And here's the geometry of the optimal design. And this is fairly close to the design of the prototype that was built. The inneron and outeron are slightly different sizes than what was come up with just based off intuition, and would save roughly 3% of drag, which, while that seems insignificant, that is actually a fairly significant saving if this was to be flown regularly.